So yeah, we'll be doing a bunch of stuff hands-on with Jupyter Notebook. So I'll give you time for some exercises. We're a relatively big group, so it's going to be a little bit hard, but I'll try to walk around and help you. Oh, two small corrections to the introduction. I'm now at Columbia University, not at NYU anymore. And also, it's pronounced scikit-learn. Maybe you can all say together, scikit-learn. OK, there's a lot of people mispronouncing the name. It's kind of tricky. I didn't come up with it. But scikit-learn, sci stands for science. All right, so let's get started with the intro to machine learning. So first of all, what is machine learning? So the idea of machine learning is to extract knowledge from data. And the way I think about it, it's mostly about making predictions for new unseen data. There's very different kinds of machine learning, and there's a large overlap with statistics. But sort of, for me, the core of machine learning is you have a data set for which you know particular outcomes, and you want to generalize this knowledge to new unseen data for which you don't know the outcomes. There's actually three types of machine learning that are commonly used. We're mostly going to talk about the first one, which is supervised learning. So in supervised learning is exactly the setting where, let's say you want to detect are emails spam or not. You start with a data set of emails. For each email, you have a human labeled whether they are spam or not. So you have the input together with the target outcome. And then you can learn a machine learning model that will allow you for a new email to say, is it spam or not? That's supervised learning. During training time, you have the desired outcome. In unsupervised learning, it's a little bit less structured. It's usually someone just hands you a data set, and you're trying to perform some modeling of the data set. Often this is for visualization or for exploratory analysis, or it is for compressing the data set, dimensionality reduction, or clustering. We're going to do a little bit about that, but not as much. The last type is reinforcement learning. I mean, there's 20 more subtypes of each of these, but sort of the three big types of these. And reinforcement learning is about an agent learning to act in an environment. And you might have seen the two most prominent examples of this right now are probably AlphaGo, getting better and better at playing Go by playing itself, and self-driving cars learning to drive in an environment. So here, there's no training data per se. There's an agent and an environment. The environment can be the real world. It can be a Go board. It can be like a video game or anything. But there's an agent interacting. And we're not going to talk about this at all today. We're mostly going to focus on the supervised learning part. So I'm going to talk. OK, so I'm going to talk mostly no math, but a little bit of math. So who here has some background in probability theory? OK, a little bit more than half of the people. So if you don't understand what I'm saying, it's not that bad. You can still do machine learning. If you understand what I'm saying, good. So the setting for supervised learning that I'm talking about usually is you have some data points, x and y. So let's where x describes the data and y is the desired outcome. So in the example, x is some description of an email, and y is 0 or 1, spam or not spam. And you have many data points that are drawn from a distribution IID, means they're generated sort of by the same process. So you just collected a bunch of emails randomly. But that means they are basically, each of them sort of has the same role. There's no special emails or something like this. And then what we want to do is we want to find some function that allows us to say for each that is like our machine learning model, which I called F here, which allows us to say for a given email, it'll tell us 0 or 1. So this is sort of the collection of data points. Oh, by the way, if anything's unclear, please interrupt me. We have a lot of time, so I'm very happy to answer questions in between. And so there's two main subtypes of this. Why is this discrete? It's called classification. So this is like spam or not spam, or this person will click on the ad or not click on the ad, or this image contains a rabbit or a duck or a cat. The other one is, so this is for my students. So the example for classification was, will they pass the exam? And the example for regression was, how many points will you get? So in regression, you're trying to predict a continuous outcome like for example, the value of a stock, or how much will a person buy, or how many people will move to a new apartment you're going to build. And so, so what I said, the core point of machine learning is not only build a model for the data you have, but also generalize to new data. So the point is not to learn about the data for which you already know it's spam. The point is, if a new email comes in, you want, without human interaction, you want to be able to say, is this email spam or not, and then move it to the spam folder, or do something else with it. And so, okay, so this is sort of the basic setting we're going to talk about actually most of the day. Is you have a bunch of data points, they're all generated IID from some distribution, they're all like generated by the same process, and we want to find a function that can generate this output approximately for new data points created by the same process. Maybe one caveat here is that you really assume that the data that you trained on and the new data that you want to predict on comes from the same distribution or was generated by the same process. That means if you trained your email spam detector only on like personal communications, then it might not work for like newsletters. Or if all the emails you trained it on were your buying notifications from Amazon that tells you you bought something, then it'll not work on anything else, and it's going to be relatively useless. So you need to make sure that whatever data you collect to train the algorithm with reflects the data you want to use it on later. Okay, so the thing we're going to use for this is scikit-learn. So this is a Python library. So who here has used scikit-learn before? Okay, all right, a bunch of people. So we're going to dive relatively deep into how to use scikit-learn. So it's a library that provides a bunch of models for doing classification, regression, clustering, and so on, all kinds of different machine learning tasks. It also provides to glue, to build them together to coherent application, to build pipelines, to do evaluation, and to tune parameters of models. So I was introduced as the core developer, so I'm one of many core developers of scikit-learn. There's right now, I think there's 42 people. No, actually, since yesterday, there's 45 people part of the core development group. I think each month there's more than 50 to 100 people contributing. So this is a giant open source project, mostly run by people on their volunteer time. I mean, I've been on the project for 6 years now, but the founders have run it for like 8 years at least. So you should get involved if you're interested in machine learning. There's lots to do. All right, so now, sorry, there's a typo on this. So now I want to start jumping into the notebooks and do some hands-on stuff. We're going to start very simple with just data loading. I hope you all got the notebooks and got set up. While we do the exercises, if you have any problems with the setup, any questions about the exercises, please raise your hand. I'm happy to come help and see if we can figure things out. Oh, and while we do any of the hands-on exercises, check out scikit-learn.org. There's, in particular, there's the user guide and the API documentation and the examples. These are 3 things where there's a lot of material, as will be really helpful for you for doing any of your hands-on exercises. So if you click on documentation at the top, you get to this, or you can directly click on user guide, API, or example gallery. So, okay, actually, before we jump in, I want to talk a little bit more about how we represent data in scikit-learn. This is more generally how people usually do it in machine learning, but specifically the scikit-learn interface. So in scikit-learn, all data is float data, so it's continuous data. So when you put something into scikit-learn, it's assumed it's a matrix with continuous numbers. So if you want to put in an email, you have to do some work. And later on, we're going to talk about how you're going to do this. But by default, everything's assumed to be floating point numbers. And you have a matrix that's a two-dimensional matrix or NumPy array. And each row is one sample, so one thing you want to reason about, say one email. And each column is one feature or one characteristic. So maybe it's more easy to think about this. Let's say you want to predict whether a user will click on an ad. Then each row would correspond to a user. And the first feature might be the age of the user. The second, how often they visit your website. The third, how many ads they clicked on before. And so on. And so this is the structure we will always have for all algorithms. So we have a NumPy array, number of samples times number of features. And if we do supervised learning, we will also have an output label that we call y that is just a number of samples. It's usually a 1D vector. And so yeah, so we'll always, use x and y for data and targets. So it's maybe not the most intuitive, but it's like a bunch of mathematicians wrote this, so we have single letter names. The other very important concept for doing supervised learning is, so I thought we want to generalize. We want to learn from data and generalize to new data. And we want to make sure our models actually work. So we don't just want to build a model, put it in production, and then realize it's not working at all. So what we're usually doing is we split our data up into what we call a training and a test set. And the training set is the one that we use to build the model. And the test set is the one that stands in for our future data. So we pretend we have not seen the test set yet. And the test set emulates the future data that will arrive, and for which in the future we will not have the labels. For the test set, however, we do have the labels. And so we can evaluate how well will the model do. So that's a crucial part. So, and usually, while we split our data set, there's a method that we'll see train test split that takes like 75% for the training data, 25% for test data. You build your model on the training data, and you apply it to your test data. This is really crucial, because if we would use all of our data to build a model, then we would have no way to know how well it performs. And we're going to do like more fancy stuff later on, but this is sort of the most basic thing you can do to assure your model works reasonably well. All right, so now let's actually go hands-on. So hopefully you all got a folder that looks something like this. So you can start it with running Jupyter Notebook from the folder that you downloaded, or if you're Windows users, from your menu. And so we're going to start with 0, data loading. And it should look something like this. Can you guys in the back see this, or should I make it larger? It's OK? Cool. So we're going to start out with some data that's built into scikit-learn. Later on, we're going to just start reading from some CSV files. But to get started, we just want to get our hands on some data. One of the data sets we will be using is a small toy data set called digits. This is a bunch of handwritten digits. To load this data set, we'll use the load digits function from scikit-learn.datasets. So here I import the function, and I call it, and I get back this object digits, which is something like a dictionary. It contains data, target, images, description, target names. So here the data is about 1800 times 64. So as I told you before, the shape of the data is always number of samples times number of features. So it tells you here we have 797 data points, and each of them is described by 64 features. And then for each of those, we have a target that we want to predict. So we also have 797 targets. We can look at what these targets are, and they're the numbers 0 to 9. So this is just the first three and the last three of this very long vector. I can call bin count on it, and it will tell me how often each number appears. And we see okay, each number between 0 and 9 appears about 180 times. So this is a classification task where the task is to predict one of these 10 classes, and the inputs are 64-dimensional vectors. And we can understand a little bit better by looking at the 64-dimensional vectors in a slightly different shape. These are actually all 8x8 grayscale images. So this is just the first column of this data, sorry, the first row of this data matrix reshaped to an 8x8 matrix. And you can see it's like a super low resolution version of the digit 0, in which if we look at the target, we see it's 0. So the goal here for this data set is to go from this very low resolution grayscale image of a handwritten digit to the actual digit class. So the 10 class classification problem. And here, so the features are the grayscale value at this position, the grayscale value at this position, the grayscale value at this position, and so on. It's the simplest and most stupid way to try to build a machine learning model from this image. So here are a couple more of these images just to show you what they look like. So there's going to be a bunch of matplotlib code, which is sometimes a little bit tricky. I don't want to go too much into detail in the matplotlib code, but if you have questions, please let me know. Oh, maybe one thing that's important is you should, if you want to have the things show up in the notebook, you need to either put matplotlib inline or matplotlib notebook in your notebook. So the inline will just show you a PNG image, and the notebook will give you an interactive interface. And you should use one of the two in each notebook. Yeah?
Right. So I don't have a question specifically on this here, but just in general, since this is getting started, if someone were to not choose scikit-learn at this point, what would be the, what other frameworks might they be starting and why why would they choose?
Okay. So maybe I'll repeat the question for the video. So what other interfaces or what other tools are there out there, and why would they choose scikit-learn? So I think in Python by now, it's there's also Orange, which is a little bit more GUI oriented. So I don't really know of any data scientists that use Orange, but that might be because I mostly work with people that like to code. Otherwise, I think in Python it's pretty much dominated by scikit-learn. There's a bunch of different tools out there in R, for example. There's MLR, there's Caret. There are mostly things that pack together many different packages. There's commercial frameworks that are, or semi-commercial frameworks like H2O, which works for Python and R. And then there's, if you run on Spark, there's, they always keep renaming it. I think it's called ML now, Spark ML or something like that. So the thing is, so if you're a beginner, you really want, okay, you're not going to talk about doing something on Spark or something like this, so you probably want to do Python or R, which are both, I think, good choices. It depends a little bit on what your environment is, what your coworkers work on, what other people in your research field work with. I'm a Python guy. I don't really want to go into Python versus R. It's more a matter of preference and community. So one thing that's kind of nice about scikit-learn is it's has quite a bit of documentation, a consistent interface, and a big community behind it. If you will look at the documentation that's available for Caret and the documentation that's available for scikit-learn, I think the scikit-learn documentation is better. If you look at the documentation that's available for the tinyverse and the documentation that's available for pandas, then the tinyverse probably does better. But yeah. So it's more like an ecosystem versus ecosystem thing. So there's all the other stuff in Python for deep learning. If you get started, don't start with deep learning. Try to know how to learn a linear model before you do a deep learning model. Don't use scikit-learn for deep learning. For deep learning, I would recommend using Keras with either Tiana or TensorFlow backend. It's great. We're not going to talk about it today at all. That's like a whole different class. Definitely learn Keras. It's amazing. OK, did I answer your question? Okay, and went off on 3 tangents. So I really want to, well, I only talk for 20 minutes. That's not too bad. All right. So before we get going, as I said, important part is splitting the data set into a training and a test part. There's this method. This is actually, fun fact, this is the most commonly used function in scikit-learn. You can implement it in like 3 lines of Python, but it's the most commonly used function in scikit-learn. Train test splits your data into training and test set. So here I give it the digits data, which is the number of samples times the number of features, NumPy array, and the one-dimensional NumPy array with just the targets. And it spits out train data, test data, training labels, test labels. And by default, it uses 25% for test data, but I can also say something like, I think it's tests. And then I get a different size. So the default is 25. And so you can see that before we had this amount. Ooh, sorry, I wanted to do data. And then afterwards, we have 2 and these are randomly selected from the data. Oh, so one thing where maybe something comes in that I said earlier about the data being all generated by the same process. There are also, scikit-learn generally assumes there's no order to the data. If you have a time series and you just did this, you lost the complete structure of the time series, and all your results will be invalid. So make sure that your data is actually not ordered. All right, so this was like very simple to know. What I would like you to do is load the iris data set with the function load iris. Find out what are the number of features, what are the number of samples, is it classification, is it regression, what is the number of classes if it's classification. You can look at the data set in the Desker attribute if you're not familiar with it. And if you then have a little bit more time, you can also try reading it from a CSV file. So there's a CSV, so you can get the path of a CSV file here, and you can try to see if you can extract the data set from this CSV file. But first, try to do the simple route, which is with load iris. So I think for nearly all of the exercises today, there will be solutions. Don't load the solutions. Try it yourself. You can uncomment this line and run it and load the solutions. You will lose a lot of what you can get out of the workshop if you load the solutions. This is like a very warm-up exercise, so I'll give you 5 minutes for it. But if you have any questions or any setup problems, I'll walk around and help you with setup problems or with any other problems you have. Questions? OK, cool. So, yeah. Okay, we start pick up in 5 minutes. Yeah, they were. So you need to load digits. So, oh. OK, so maybe one thing. So who here has not used Jupyter before? I'll come back to you in a second. Who here is not? OK, sorry. I should have. Let me tell you, if you have used Jupyter before, ignore me. Whirlwind tour of Jupyter. So each of these cells contains code. You can run the code by pressing play up here and see the output. You can also run the code by pressing Shift and Enter. And so what I'm doing is I run through the code, and I press Shift and Enter each time. And so it executes one of the other cell. If you forget how to do anything, press letter H. It'll give you all the shortcuts. You have to do this while you're not in a cell. So you click somewhere that's not a cell, press H, you'll see all the shortcuts. The other thing is you can get help if you're, for any function call. Let's say I don't know what bin count does. one way to get help is type a question mark after it and then press run or shift enter, and I can get the doc string here. The other way is I can do open and closing parentheses and press shift and tab, and I see the doc string in line. And if I press shift and tab multiple times, I see more and more documentation popping up. So the idea is that if you, while I would talk to the code, you run the code in parallel. So you can't, all the code depends on each other, so you can't just run the last cell. You need to run all the cells before. Okay, I'm going to move on so that not everybody starts reading their email, but there will be more exercises, and if you still have setup trouble, I'll come around. So this is like a data set that's nearly 100 years old now, I think. Fisher, like the famous statistician, collected this. It's about irises, but so we can load it with load iris. We can get the data in the target, which I call x and y. And so the shape of x is 150 times 4. So there's 150 data points, and each is described by 4 features. Y is then obviously also of size 150. And there's 3 different values in y. So it's a classification problem with 3 classes. I also did like a small plot of the first feature against the second feature and the second feature against the third feature on the training data. So basically, a good thing to do before you do any analysis is split your data into training and test data and do your analysis only on the training data. And so that's what I did here. And so maybe a bunch of people tried to use read CSV. So I didn't have that in the solution here, but so the thing that you'll notice here is the column names don't really make sense. So if you can get the description of the data set. Here. And so this will tell you what the 4 features mean. There's like measurements on a flower, sepal length, sepal width, and so on. And so these are actually the 3 class names. So in this CSV file, the first line of the CSV file is the number of samples, the number of features, and the name of the 3 classes. This is not the header of a CSV file. Whenever you get a CSV file, assume it's broken. So the correct headers here would be, this is sepal length, sepal width, petal width, and this is the class. And then if you did this, okay, so let's say we can, okay, let's say I skipped this because it was not really helpful. Then I can I want to separate the data from the target because scikit-learn has them separate. And so that, the way I could do it, for example, is y is data.pop5 and x is data. And then we hope it works. No. That's what you get for live coding. Come on. Yes. I'm not very good with pandas. There we go. Okay. Okay, now it's good. So I got the last column and put it into Y. This is the classes. And then the first 4 columns are the data. And so from here on, I could then do train, test, split, and get my training matrices and my test matrices. Yeah? Sorry? Yeah. I don't understand the question. Sorry, can you?
So if you sort on, say, X, right, that array, would it mess up how it matches with the target Y?
So the train test split shuffles all the rows, but it shuffles the X and the Y accordingly. So they correspond. They will not correspond to the order in the original X, but the rows in X train and X test will correspond to the outputs Y. Does that answer your question?
Yeah, because I'm just wondering if you have 2 data sets and you have another data set with the target, and then you have the data set in your target, and say it's ordered in one way, and then in your X it's ordered a different way. You want to probably sort it so that it's correct, and then you do this test train split,
Yes.
right? But then after you do a test train split, you don't want to do any manipulation.
Yeah, I mean, generally, you probably don't want your data set to be ordered in any way. And
Right.
if there's a way to order it, then that's natural. That probably means that there's some structure to the data, and you need to think about how to deal with that structure in the data. But that's like a more advanced topic.
Thank you.
But you don't want it to be ordered by class, for example. That usually messes up things. So here, shuffling the data so it's not ordered by class is something that is kind of important. Otherwise, if you just take like 25% and the 25% that you take off are all the last class, then your results will not make any sense. All right. Other questions?
So I noticed that you say pandas. So when you do the train test speed, it's also pandas.
Yes.
But when you enter in the scikit-learn, should you keep it a pandas or keep it as a
All right. The question is, if we start with the pandas data frame, we put it into train test split, we get the pandas data frame out. If we put it into scikit-learn models, which is the next thing we're going to do, should it be a NumPy array or a pandas data frame? Right now, it should everything should work with pandas data frames. So, but you need to make sure that all the entries are continuous. If any of them are categorical, they will be treated as continuous, which is not what you want, and we'll talk about that later. If any of them are strings, it'll crash. So make sure everything is float, then you can use a pandas data frame. If you do any transformation with scikit-learn right now, it will lose all the column names. So it will completely ignore the names of the columns, and it'll drop them, basically. But also train test split will always try to output the same thing that you put in. So if you give train test split lists, it'll give you lists. If you give NumPy array, it'll give you NumPy arrays. If you give it pandas data frames, it'll give you pandas data frames. All right. So let's move on because we've got a lot to cover. So next what we want to do is we want to do some supervised machine learning. So as I said, we start out, we have some training data and some training labels. We use these to build a model, which is like any machine learning algorithm. I'm going to talk about different kinds of algorithms a little bit later. For now, just let's assume we have some model that can learn and can make predictions. And then if we get new data, test data, we can use the model, we can make predictions on the test data. And if we have the labels for the test data, we can validate whether the predictions by the model were accurate by comparing the test labels to the predictions. This is sort of a very standard supervised machine learning workflow. And there's 2 phases. There's the training of the model, and there's the applying the model to new data or generalization. And here's how this corresponds to the scikit-learn API. So the API for all models in scikit-learn is basically the same. You always start by first defining the model that you want to use. They're all implemented in Python classes. So for example, let's say I want to use a random forest classifier. I can instantiate the random forest classifier. I get an object, CLF. This object encapsulates the training method, the prediction method, and it will store everything that is learned from the data. So basically, it encapsulates both the algorithm and the result, or the model. Then we can call clf.fit. This will build the random forest model. The parameters to fit are always the data and the labels. So I give it xtrain and ytrain. This will build the actual model and store it in a CLF object. Then I can use the CLF object and make predictions on new data, xtest. Of course, this needs to be like from the same data set. It needs to have the same number of features with the same semantics and so on. And so ypred now would be for classification, the classes that the model assigns to the rows of xtest. I can also use the model directly to score how good the predictions are with the clf.score. What that does is basically just it runs predict and then compares the output to the known labels in ytest. For classification, score always uses accuracy. For regression, it always uses R-square. And we'll talk about different metrics later on. But so this is sort of the most basic way to apply machine learning algorithm with scikit-learn. You instantiate the model, you train it on a training set, and then you predict it on you either predict on a test set or you just evaluate the algorithm. Yes. Yes. So, yeah, clf.score applies prediction to the test data and then compares it with the known labels and then returns accuracy. All right, so let's try this. So now I'm going to go to Introduction to Scikit-learn. So we're going to start off with the same thing we did before. We're going to use the digits data set. I'm going to use train test split here on the data and the targets. So one more thing. So the train test split shuffles the data, and it does so randomly. And so it has a random seed that says how is it going to shuffle it. And if you want your results to be reproducible, so if you want to make sure that every time you run this, the data gets shuffled in the same way, you can set a random state to some number. If you set it to a different number than me, you'll get different results, which is not bad, but just to be aware of. All right. So here we have our data set with the 64 features, 1,300 training points. The first model we will apply is linear support vector machine. As I said, I think in the afternoon, no, in like after the coffee break, like in an hour or something, we talk a little bit more about how these models work. For now, just take the model as a model. So we import it. You can find in the documentation, in the API documentation, all the different models. There's like tens, maybe 100. First step is instantiating the object. So now we have the SVM object. This is when you would set any hyperparameters. Most machine learning models have some kind of hyperparameters you need to tune. But you can always just sort of instantiate the object. Then we fit the object, which is done in this line. So this did the machine learning. Running this line was the machine learning part. And now we can apply the model. So what I'm doing here is I call predict on the training data set, and I compare it visually against ytrain. And you can see they look the same. can also call it score. And this is accuracy, so it says in 99.6% of the time, the prediction on the training set were the same as the true outputs on the training set. So what this says is the model, oh, do I need to zoom in more? I need to scroll up. OK. The predictions on the training set were 99.6% the same as the true labels. That means the model was able to learn the training set by heart, which is not really our goal. Our goal is to see how well it can generalize to new data. And so we can see how well does it do on the test data set. And the predictions are 93.5% accurate, which is pretty good. This data set is like a toy data set and very easy. So anything will do pretty well on it. But this is sort of the basic workflow. So let's do the same thing again, but with a different model. This time, we're going to use a random forest classifier, one of my favorite models. So we import it. We instantiate the model. Here I'm setting some parameters. I say the number of trees in the forest to 50. And then I can fit the model. So this will build the model and store everything that was learned, all the trees in the RF object. And then I can do rf.score. And it tells me it's 97.5% accurate on the test set. So this one did quite a bit better they both did pretty well with high 90s accuracy, but this is doing pretty well in this data set. All right, so what I want you to do next is, again, load the iris data set that we loaded in the last exercise, split the data using train test split, and then train and evaluate the classifier of your choice. You can either use the linear RCC with here or the random forest classifier, or you can check out the kneighbors classifier, which you can import from scikit-learn.neighbors.kneighbors classifier. Yeah. Run any of them, train them on a training set, test it on a test set, see how it goes. Don't load the solution. And so, again, I'm going to give you 5 minutes, and this time I'm actually going to check out my watch. OK, I'm going to say it for everybody. OK, who's still working on the assignment? OK, most people are done. So I have a couple of very good questions that I'm trying to answer. Some of them I'll answer later. So the most common question was, the random state was the same, but I still got different answers. Why? So the random state here is for splitting the data. But many of the algorithms themselves are also randomized. And for some reason, even the linear support vector machine has a randomized solver. So if you set a random state here, then the results should be the same. You can see the results changed now when I set the random state. And so there's some randomization. So actually, for this model, it usually doesn't matter that much. For the random forest, it's like a very, very randomized model. I mean, it's in the name. So this also has a random state, so that you can set if you want it to be reproducible. And then you'll have the same results as me, at least if we have the same version. If we have very different versions of anything, then that might not work. Another question that I had, I think a good question, particularly if you come from R. So train test split does nothing but splitting the data set. And none of these models do anything else than what their textbook version says, basically. So the random forest trains the random forest. The SVM trains an SVM. There's no standardization or cleaning of the data, or no treatment of categorical variables, or missing data, or anything like that. You have to do all of this yourself, which means you have a lot more control than in other situations, maybe. But it also means that it's a little bit more work. And we're going to talk to all of these. But basically, all of these algorithms assume that you cleaned your data. They don't do anything automatically for you, basically. So the question is, if there's a NaN, what's going to happen? It's going to crash. Actually, it's going to crash. So we put a lot of effort into them crashing very often, giving you good error messages. There's actually a bunch of tests that check if you give it invalid input in one way or the other, does it give you a good error message? And yeah, we worked on this for a couple of years, and hopefully it will give you a helpful error message. There was one more important question. Well, it'll come up again. OK. So here, I mean, this is basically the same we just did before. Just wanted you to run through it yourself. Oh, the other question was, how can I make sure that if I do the training and test splitting, the frequencies of the classes are the same in the training and the test part? So in real-world settings, very often you have unequal class sizes. Let's say if you do ad click prediction, 99% of the time, the people don't click on the ad. So you have 1% of your data is the person clicking on the ad, 99% of data is the person not clicking on the ad. Doing machine learning, this setting is slightly hard, and we're going to talk about it in the afternoon probably. But one thing that you want is if you do a train and test split, you want to make sure that both in the training data, 99% is non-click and 1% is click. And in the test data, 99% is click and 1% is click. If you just split randomly, if you have such an imbalance, it could very easily happen if you just do random splits that there's no click data in the test data, right? Because only 1% of the data is click. And that would make your evaluation completely worthless. And so there's an option to make sure that if you split your data set, you split the classes proportionally, and it's called stratify. And you have to say what to stratify on. So if I say stratify equal to y, it will stratify on the entries of y. That means the groups defined by y will have the same distribution in training and test. If this confuses you, don't worry about it now. Otherwise, this is best practice. But it's not the most crucial detail. All right, so this is the same as we did before. We load the iris data set. Data is x, labels are y, train test split into xtrain, xtest, ytrain, ytest. I do the k-neighbors classifier, which with 3 neighbors. I call fit on the training set and score on the test set. And that's it. Questions? Yeah. Yes, so the prediction function is called in the score function. So if I just want to evaluate, I can just call score. If I want to have the results, I can call predict. Yeah, if you use score, this is like just a very quick way to evaluate. There was also questions, are there other metrics? There's a tons of other metrics. We'll talk about it in a little bit, like confusion matrices, ROC curves, precision recall curves, whatever, everything. Other questions? Cool. So while we're going to be mostly talking about supervised learning, which I think is the most successful kind of machine learning, I also want to talk a little bit about unsupervised learning, which will basically give us the complete interface of what is in scikit-learn and all the ways you can use scikit-learn. In unsupervised learning, as I said before, basically someone gives you a data set and says, build a model of it. And this, typically, it's like feature extraction, dimensionality reduction, or clustering. I'm not going to go too much into detail for these. And then for some of these unsupervised models, they create a new view of the data. Think about principal component analysis, for example. And then you can take your test data and apply this new representation, this new view of the data to the test data. This is what I call unsupervised transformers. And the way this looks, here's for principal component analysis. If you don't know what that is, don't worry about it too much. I'm going to go through some simpler examples in a second. So here, as before, we instantiate the object. Then we call fit. Here, this is an unsupervised model. So there's only data, no targets. So there's only x, no y. The reason why I called them train and test here is because let's say we want to do this as pre-processing for some supervised learning afterwards. Then we need to have training and test data. If we just want to do unsupervised learning, we don't necessarily need training and test data. It depends. OK, so we call fit with the training data and no labels. And then there's a new method called transform. And transform transforms your data into a new representation. So here it projects on the principal components. So x new has the same number of samples as x test, but it has potentially a different number of features. All right, so these are basically, there's 3 really important methods in scikit-learn, which are fit, predict, and transform. And that's basically all of it. It's like 90% of the interface. OK, so let's go to the unsupervised notebook and walk through that. Yeah?
So for supervised learning, we want to use predict to generate the output.
Yeah.
For unsupervised learning, we use transform to get the
So it'll all become clear. But now, so transform is actually predict and transform are not so much supervised and unsupervised, but predict is if you want to have like something like a y. So if you want to do regression on a target or classification, predict is actually also used in clustering, where you want to output a cluster label. Transform is used whenever you want a new transformation of your data. I have an overview slide of this later, but basically here, it's a new view of the data set. And so also if you do feature selection, which can be supervised, you'll also use transform. But we're going to go through a couple more examples now. So here I start again with loading my digits data set, splitting it into training and test data. And so the simplest transformation that I can think of is removing mean and scaling the variance. This is not really what I would call unsupervised learning, but it's the same style of transformations. We learn a transformation from a training data, and then we can apply this transformation to the training data or to new data. Only transformation is very simple. So removing mean and standard. So the question that I usually get here is, why do you want to do this? So for some models, it's better if you scale the data. And we'll talk about this later in a little bit. But let's say we want to scale our data to remove mean and make the standard deviation 1 for everything. This is implemented in the standard scaler in the preprocessing module. And again, as before, we instantiate a model, and then we can fit it on the training data. And so this basically just computes mean and standard deviation on the training data. Then we can call transform on the training data, and it will return a scaled version of the training data. So here, you see the shape of the data is exactly the same as you would expect. It's just the mean was removed and was scaled by the standard deviation. So if you check out the mean of x, it's this. If you check out the mean of x scaled, it's 0, like float equal to 0. And if you look at the standard deviation, it's mostly 1. There's actually a couple of zeros in there because some of the pixels in the drawn digits are always white. And if they're constant, you can't get them a standard deviation of 1. All right, so here, so the fit step just computed mean and standard deviation on a training set. Transform applied it to transform the training set. Now we can use the same to transform the test set. So let's say this is pre-processing for some supervised model. OK, so any predictions of what the mean is when I compute the mean of the transformed test data? 0? Who says 0? Who says something else? No? One person. Good job. So the thing is, with preprocessing, you want to apply exactly the same transformation to both the training and the test data set. This transformation here is removing the training set mean and scaling by the training set standard deviation. The training set mean and the test set mean will be slightly different. So if I subtract the training set mean from the test data, the mean will not be 0. It will be around about 0, but not really 0. If your data set is infinitely big, it'll be 0.
So during the model building, if I do the preprocessing with the training data and use the same model to process the test data, is not some information being leaked out from the training to the test data?
What do you mean by information from the training to test data? I mean, you're extracting all the information you can from the training data, right?
Yeah, but then say I'm doing the normalization and I had a value of 99 of some value to bring into the mean equal to 0, right?
Yeah.
Now that value is applying to the test data again. So somehow I let the test data know that training data has this 99 or something.
Yeah, you also let the test data know about everything about the training data because your whole model is built on the training data, right?
It's like the same distribution, right?
Yeah. So I'm not sure. All the information from the training, I mean, the whole point is to pass as much information from the training set to the test set as possible, right? That's like what the learning is doing. Maybe you can talk offline. I'm not sure I understand the question. Yes, it's the reverse you want to avoid, yes. You don't want any information from the test data to leak into the model, basically. But this? Oh. This is, so X test transformed is number of samples times number of features, right? And so I want to compute the mean over all the different samples. So this now, the shape of this is 64 because I computed the same, x is 0 is the sample, so I compute the mean over all the samples. If I do x is equal to 1, I compute the mean over all features, and so the shape will be number of training points, so like 17,000. Oh, this test data set, sorry, 400 something, yeah? Yes, this is the mean over all the columns. The other one, and if I don't put an axis argument in, it'll be the mean of everything, which will be just a number, which will be not very interesting. So I wanted the mean over the rows. All right. So moving on to some slightly more interesting transformation. So I don't think we have time to walk through the details of principal component analysis, but so what it does a linear transformation of your data that retains most of the variance, or as much variance as possible. You can think of it as fitting a high-dimensional Gaussian to your data, and then looking at the two axes with the most variance, and then just keeping these. So it's often used for dimensionality reduction, and by default, it'll extract all principal component, which is as many as there are features. I can set the number of principal components I want to extract, like here, at instantiation time, as always. So here I say I want to extract the first two principal components. Then I fit the model. Here I didn't do a split into train test data because I'm only interested in like doing exploratory analysis. All right, so, and then I can do transform to project on the principal components. So before the data was like 1800 times 64. Now for each data point from the 64-dimensional space, I projected it down to a 2-dimensional space. The reason why I picked a 2-dimensional space is because my monitor is 2-dimensional, and now I can visualize it. I'm really looking forward to the day when I can buy a 64-dimensional monitor. Data science will be so much easier. So what I'm going to do is I'm going to do a scatter plot where the axes here are the first principal component and the second principal component. This is a completely unsupervised method, so this projection was computed just from the data without any class information. But what I'm doing now is I color the points by the class. So there's 10 different digit classes, 0 to 9, and now I color the points by these classes. So basically, so we can see a little bit what's going on. And you can see, I mean, there's like sort of 10 different like blobs here. The brown, I'm not sure which number it is. It's probably a 7. It's scattered all over. But a couple of them are really separated well from the rest. So this gives you some idea of which classes might look similar, which classes might look not so similar. And you get this representation just by doing completely unsupervised transformation of the data down to 2 dimensions.
So in this case, we already know the class, right? Based on those colors.
Yes.
Some class like digit 1, 2, 3,
Yeah.
so this is supposed to be a supervised learning because you already know the class label.
I mean, that I know the class label doesn't mean I have to do supervised learning. The transformation I learned here is unsupervised. So I didn't, like in learning this projection from 64 to 2 dimensions, I didn't use the class labels.
So what you say is the PCA belongs to the unsupervised.
Yeah, the PCA is unsupervised. I just used the labels here for us to make a better picture that's more meaningful. If I take the colors away, it's much less interesting. And then you wouldn't see what's happening at all.
So what is the scalar plays a role in this whole process?
The scalar, oh no, this is just a different application of
I mean,
a transform.
before the applied PCA, right?
Yeah.
Do we apply the scalar?
I mean, actually it would probably be good to apply the scalar before you apply PCA. I didn't do it here. I just want to show you 2 different situations where you might want to use a transformation. Like the scaling the data is a very common transformation, but it's kind of boring. This is a somewhat less common transformation that actually does unsupervised learning. Yeah, it's less common, but it's more interesting. So I want to talk a little bit about another unsupervised algorithm that's even less common, which is, or a class of algorithms, which is called manifold learning. Manifold learning is really done only for exploratory data analysis and visualization. So PCA can be used for a lot of different things. It's very versatile. But manifold learning really is just for visualization. And there's a whole module in scikit-learn about manifold learning. Most of these algorithms can only transform the training data. They cannot transform new data. So this is one of the reasons why they are not really used for, like, as pre-processing for supervised learning, for example. They're really just for making pictures. So one of them is called isomap. It's kind of a classical one. And so because they can't transform new data, they don't have a transform method. But they have a fit transform method that fits the model and already transforms the data that it was fitted with. So it does both things at once. And so the result of this is X isomap. So this is like, and the manifold learning algorithms, they always project to 2 dimensions because they're done there for visualization. And so now I can plot this again, and you can see that it did a somewhat better job on separating the data sets, the different classes in the data set. So here, manifold learning algorithms, they project the data to lower dimensions, but they do so in like really weird ways. So the 2 axes here don't have any meaning anymore. Like in this one, the axes are pretty clear. They're principal components. If you know a little bit of linear algebra, then you can understand what these axes mean. No amount of math can help you understand what these axes mean. They're completely meaningless. Well, not completely, but they're nothing that would actually help you. So what I would like you to do is do the same thing I did with isomap here with another algorithm that's kind of trendy, which is called TSNE, which stands for Student T Stochastic Nearest Neighbors Embedding, I think, something like that. And apply this to the digits data set. So just load the digits data set. You don't really need to split it. Just use the whole data set, do a fit transform, and then plot it. And I think there's a coffee break at 10:30, so maybe you can do this, and then we go into the coffee break. And I'm mostly going to stick around, and I'm happy to answer any questions. All right, so I just want to come back real quick to this exercise about doing manifold learning with t-SNE. And I mean, the code is basically identical to the one we did here. And the idea is we instantiate the t-SNE model. We call fit transform on x. We get a transformed version of x, which is now two-dimensional. And we can scatter it. And basically, the first time I saw this, it totally blew my mind, because this is a completely unsupervised algorithm. But it basically did a perfect job of separating the different classes. And this is, as I said, this is like a simple toy data set. But this looks very different from what PCA created. And now, it's a little bit tricky to do this with this figure. But you can try to look at what are the orange ones down there. Are they different from the other orange ones? And I think these are the different kinds of 9s or 7s that are like drawn slightly different ways. And sometimes it separates the two with like a little bow on the bottom, whereas the ones that don't. But it mostly just nearly perfectly separates all the different classes, even though it has no access to the class labels at all. And so I think that's pretty cool. The question that always comes up here then is, can I use this as pre-processing for supervised learning? And so if you want to do nearest neighbor on this, it's probably going to work better than doing nearest neighbors on the original data, even though you're reduced down to 2 dimensions. But if you're actually interested in building an accurate model, so then doing, say, random forest or gradient boosting or neural network on this will perform worse than the original data. So if you're actually interested in doing supervised learning, don't do this. This is just for pretty pictures, but it makes very good pictures. So that's why I think it's kind of nice to hear about this. It's also used for like text data and different kinds of data. Generally, it does both sort of clustering in a sense, as you can see, but it also gives you some similarity of the different classes. So here you might think that orange and yellow are kind of maybe more similar than orange and blue. Or that here, these data points, they look more orange than they look blue. And so you can look at them and see if they're kind of weird, maybe. Anyhow, so these are interesting to read. It's a little bit like reading tea leaves. Sometimes it's useful, but don't spend your whole day on it. And yeah, I wouldn't use this as part of a supervised learning approach. Questions about this? Okay. So, by the way, I realized I have scikit-learn stickers, but I don't have that enough for all of you. So anyone that ever asks a question today can come and get a scikit-learn sticker. And don't come if you didn't ask a question.
How do I get a scikit-learn sticker?
You pronounce scikit-learn correctly. That's the first step. OK, so the next thing I want to talk about is cross-validation. Oh, no. First, summary of the scikit-learn API. Sorry. So there's these 3 methods that are really important. Fit, to build the model. Predict, to predict an outcome that is like a one-dimensional vector, like a y. And transform, to give you a new representation of the data set. So the way we did it, we looked at it so far, predict was supervised and transform is unsupervised. But both can actually be both. So for example, so you predict you can use in clustering, which is unsupervised, and transform you can do in feature selection, which is usually supervised. But the main distinction is the output. Does it going to look like an X, or does it going to look like an Y? Does it look like some representation of my data, or is it going to be some output that I want to predict? So that's whether you know if you want to do predict or transform. And then the difference between supervised and unsupervised is just, am I going to provide an X or an X and a Y? So unsupervised algorithms don't have a Y. And this is like 90% of the scikit-learn API. This is the really important bit. Oh, another question I got that's kind of common is, how do I get a summary of the model, and how do I find the p-value? And the answer to both of this is you don't. So scikit-learn is really geared towards prediction. It's it has quite a different approach than if you come from R. So there's no p-values anywhere in scikit-learn, and we don't really care. I mean, there's good applications where you would want that, but it's sort of not in the scope of scikit-learn. There's stats models in Python, which does some of this, but scikit-learn does not. If you want to inspect a model, I think I mentioned it before. Let's go through the PCA. So you can either do the PCA question mark, and you can get all the documentation for it. And then there's also a section here, attributes. And the attributes are sort of the things that were learned from the data. So like the components, the explained variants, and so on, the singular values. So I can learn what is available here, and then I can look at singular values, if that's what I'm interested in. But there's no like summary method. All right. But so let's move on. Oh, before we do, wait. Oh no, I think before we talk about cross-validation, I just want to talk as an example very briefly through the nearest neighbors method. So I'm not sure if you can see it. So here, this is supposed to be a two-dimensional data set with two classes. There's one features on the x-axis, one features on the y-axis. There's a red class, and there's a blue class. And maybe you can see there's like 3 black stars in there that maybe could be more obvious that we want to classify. So let's say we have these 3 new data points, and we want to classify them. The way that one nearest neighbor works, it looks at the closest data point. So here, I don't have a, can you see the cursor? Yes. Here there was like a new data point I want to classify, and I find the closest data point here. The closest data point is red, so I assign red. For this one, the closest data point was blue, so I assigned blue. For this one, the closest data point was also blue, so I assigned blue. This is sort of one of the simplest classifiers you can think about. Now you can generalize this and say, what if I don't look only at the single nearest neighbor, but at the 3 nearest neighbors? And so now I can look at, for each data point here, what are the 3 nearest neighbors? OK, 2 are red, and 1 is blue. So now I can let them vote. And there's 2 versus 1. So I say, well, I should label this guy red. Here again, for this guy, 1 is blue, 2 are red, and I label this guy red. Here, 2 are blue, 1 is red, so I label this blue. I didn't actually construct it in that way consciously, but all of them flipped their label. So whether I use 1 nearest neighbor or 3 nearest neighbor makes a big difference. And so you could also obviously try not only 1 and 3, but you could do 1 and 5 and 10 and 30. These are all the different data here, plotted different data sets, and the background is colored according to how a new data point there would be classified. So instead of having these 3 stars, now every point is a star. Like every point on the plane, I say, how am I going to predict here? So if I do 1 nearest neighbor, here I'll predict blue, here I'll predict red. And here blue again, here red. If I go to 5 nearest neighbors, over here I'm going to be predicting blue everywhere, and so on. And so you can see that with 1 nearest neighbor, there's like a lot of like nooks and edges and like a lot of wiggly stuff. If I go to 5 nearest neighbors, slightly less wiggly. And with 30 nearest neighbors, it's like relatively horizontal line with like a little bit of wiggles in there. So this is one simple example of a parameter to tune when I want to apply a machine learning algorithm. So if I want to apply this, I want to know which of these will give me the best test set performance. Because I want to predict well. So I need to choose which of these am I going to use. And there's sort of one property of this that is common to nearly all models, which is this is a parameter that controls how complex the model is. So, and by complex, I mean how wiggly is the boundary. For the 1 nearest neighbor, this is actually a very complex model because it allows to have a very complex shape for the decision boundary. So how red and blue interact is very complex, whereas for 30, this is actually a very simple model because it has a more smooth boundary. You can also see that for the simple model with 1 neighbor, all the data points in the training set that you can see here were classified correctly. The more I restrict my model, so basically requiring more neighbors to have the same color means restricting the model. The more I restricted my model, the more mistakes I make on the training set. So with 5 neighbors, I make probably like 2 mistakes in red, which are these 2. And with 30 neighbors, I make 1, 2, 3, 4, 5 mistakes in red. So I have a tuning parameter which allows me to say how complex or how simple do I want my model to be. And if I restrict my model to be more simple, I'll make more errors on that training set. Here is what happens. I mean, this is like a very small toy data set, so these are like very noisy plots. But here is what happens to training scores and test scores on this 2-dimensional data set. So you can see that when I increase the number of neighbors, the training score basically goes down. It was very high at the beginning. With 1 neighbor, it's perfect. And then if I increase it, it goes down. For the test score, it starts up somewhere. It rises until a certain point and then goes down again. And this is a very common phenomenon. So I wanted to, here's a cartoon version of it. So if I have a model that's very complex, the more complex it is, the better it will do on the training data set. If I have a very simple model, it will not be able to model the training data set very well and will be bad. But if I look at the test data set, then, well, a simple model might be too simple and will not do very well. And if I increase the model complexity, it starts doing better and better and better. But the difference between training and generalization performance will also be a widening gap. And so at some point, the performance will top. And then if I make the model even more complex, the generalization performance will go down. This is called overfitting. Overfitting means focusing too much on the particularities, on the noise in the training data set, having too complex a model that is not able to generalize well anymore. You basically, at this point, you're just memorizing a training data set. You're not learning something that will generalize. And so if we want to tune parameter, we're trying to find a sweet spot somewhere in here that gives us the maximum test set performance. Underfitting is sort of the opposite, where your model is too simple. If your model is very simple, there will be not a lot of difference between the training set performance and the test set performance, but both will be low. And this is like a very central concept of model complexity in machine learning, and it's really something sort of that you should keep in mind. Should always look at, is there like a big gap between training and test performance, or is there a small gap? And in which direction should I change my parameters? So, OK, let's say you do this. You did the train test split, and yet now you ran 10 different parameter settings. And then you pick the one that is the best. The problem, if you do this, is that you now tried the test set 10 different times. And now the accuracy value on the best parameter setting that you have is not an unbiased estimate anymore of how it will be on new data. It's sort of like a multiple hypothesis testing error. Because you use the test data to select which parameter you use, you can't use it anymore for assessing how good the model is. So one way to overcome this is actually using a threefold split of the data, where you have a training set to build a model, You have a validation set, which you use to select the model and select the parameters. And then you have a test set that you use for the final evaluation. And ideally, you look at the test set only once. And if you look at the test set only once, it will give you an unbiased, a true estimate of how well you'll do on future data.
Question.
Yeah.
If once you're done with validation, selected your parameters, would you train over the whole training set plus the validation set, or just the training?
Yeah. So the question is, OK, let's say I trained my model, I validated, I found a good parameter setting. Will I retrain my model on training and validation set? And the answer is usually yes. And scikit-learn will actually do this automatically for you. And we come to that in a second. So I really want to emphasize this point because it's really important. Because if you don't do that, let's say you have only a training set and a test set, and you try out many different models, and you find one that's 99% accurate, and you're like, awesome, my model is 99% accurate. You give it to your boss, and you say, this model is 99% accurate. I tuned it for so long. I'm really sure because I tuned the hell out of it. But then comes new data, and the new data is not the data you tuned your model on. And so your model will do much worse, and then your boss will scream at you. And so we want to avoid that. So the point of the test set is to look exactly like the new data to the model. You do not use the test set for tuning. The test set is just to tell you in the end how good will your model actually be in the future. And that's why ideally you should look at a test set exactly once and then throw it away. In practice, maybe you look at it 3 times, but the more you look at it, the worse it becomes as an estimate of what will happen in the future. Again, this only works if the future data, it still assumes that the future data looks like the test data. So if something weird happened and completely changes how your data is generated, then nothing will rescue you. Yeah? Yeah, so I assume the process that generates the data is constant over time. So the world does not change in my setting, which is completely unrealistic. But dealing with an actually changing world is really hard, and there's not really a good principled approach that I know of, except for retraining. But yeah, so here I assume I collected all this data at the same time, and now I'm splitting it up. And the data that will come in the future will look exactly the same like this data. Like the world will not have changed. Like it will not be the same data, but it will look the same. And yeah, that's an unrealistic assumption, but so be aware that we are making this assumption.
So can you monitor distributions over time and see if that's changing? Is that what you would?
Yes, you should monitor distribution over time and see if that's changing. And we're not going to go into this, unfortunately, because it's very hard. So there's one thing, the world changes, and then if you have a product and you're interacting with your users, your predictions also change how your users change. That's even worse, because it means if you change your model, the behavior of the users will react to this change. And so, yeah, that's very complicated. So we assume the world does not change, and we don't change the world. And then it works. OK, so this is like the threefold split. It's the simplest thing to do. It's very simple and it's very fast. This is actually what people mostly do when they do deep learning, because training a deep learning model is very slow, so they do this. Unfortunately, this has very high variance, meaning it depends a lot on how you split this data. And it's a relatively bad use of the data. You want to use as much data as possible in the training set, and as little in the validation test set as possible. Well, but you don't want to shrink the test set to be too little, because you want a good estimate. So maybe you basically you're unlucky and all the hard data points were in a test set, then you think you do much worse than you actually do. Or maybe all the hard data points were in the training set, then you think you do much better than you actually do. So we want to make this more independent of how we split our data. And the way to do this, oh, never mind. OK, this is an implementation of this. But yeah, OK, let's walk really briefly through the implementation of this. So this is how you would do this with a threefold split. I just iterate over the number of neighbors. So I look at neighbors between 1 and 15. I iterate it over these. I fit on a training set. I compute the scores on the validation set here with k_score. Then I find out what's the best score. It's 9.7. What's the best parameter corresponding to the score? It's 3. And so here, this is sort of, I do the argmax of the validation score, look at what was the parameter. It's 3. Then I retrain the classifier on the training and validation set together. That was the question here. And then I decided which model and which parameters I want to use. I evaluated on a test set once. And so here, this is sort of my estimate of how I think, how well I will do in the future is 96.5. This is how you could do parameter selection with a single split into training validation set. But what we usually like to do with scikit-learn is cross-validation. So what we're doing now is we are just changing the inner split so that we keep the outer split into a test set that we're going to look at one at the end. But now we're going to do multiple split for the validation set. So let's say, so here this line represents our data. And so what we're going to do is we're going to split it into equal-sized parts. Here it's 5. We call them folds. We're going to take the first fold, declared our test data set, and train on the remaining 4 folds, and test on the first fold. So we build one model, which will give us 1 accuracy value. Then we build a second model, this time using fold 2 as test set, and training on fold 1, 3, 4, and 5. And so on. So we build 5 different models, which give us 5 different accuracy values. And then we can, say, average them or pick the median. This will be more stable because now I can basically make the test set bigger, the training set bigger, while still having each data point be in a test set. So here, if I have, this is 5-fold cross-validation with split into 5 folds, which would mean my training set would be 80% of the data each time. If I use 10 folds, my training set would be 90% of the data each time. If I do 20 folds, my training set would be 95% of the data each time. So my training set can be much larger each time. And as I said, but no matter what I do, each data point will be in a test set exactly once. So this helps me protect against only randomly having only simple or only hard data points in a test set. The con of this obviously is this is much slower. I build 5 models now instead of 1 model, so I need 5 times as much computation. I can also parallelize this easily because they're completely independent, so maybe I just need 5 times more computers, which is maybe better than 5 times slower. Also, you should keep in mind the output of this here is 5 numbers, 5 accuracy values. The output of this is usually not a model. You build 5 different models, but it's not that you get, you could keep them, but that's not usually what you do. You're only interested in what is the mean accuracy value. And so now you would do this for each parameter setting. Let's see if I have an implementation of this. No, that comes next. OK, so you would do this for each parameter setting. So the overall scheme would look like this. You start with the whole data set. You split it into a training part and a test part. And the test part is the holdout part that we look only once at the end. Then the training part, we do, let's say, a 5-fold cross-validation. And for each parameter setting that we want to try, we do this. We build 5 models according to these 5 splits of the data. Then we pick the parameter setting that, on average, has the highest performance. We rebuild the model on the whole training set and predict on the test data set. And that is sort of what I would think of is the standard scikit-learn pipeline to do it. And basically, you have to do this all the time because all models have parameters. And for nearly all of them, it's quite important to tune them. Here is sort of a manual implementation of this. So that I'll show you much shorter code for this in a second, but just so that you can see how you might implement this. So cross-validation is implemented in a function called cross-val score that does the splitting for you and it just returns you the accuracy values. It does the training, so it does the splitting and the training and the scoring. So here I train my data. Oh my God, there's still a typo in the slide. Sorry. So I split my data into training and test set. I iterate over all the different number of neighbors. Then I call cross-val score with the model that has this particular number of neighbors. Sorry, here this should be xtrain, not xtrain val. So it's the train part of the train test split. And I do cross-validation of this. I say CV equal to 10, which gives us 10-fold cross-validation. So this function call will result in giving me 10 accuracy values back. Then I can compute the mean of them and append them to my cross-val scores. Now I can do the same thing I did before. I compute the maximum and the argmax. So the maximum was this. The argmax is 3 neighbors again. And so now I can retrain my model with the best parameter setting and score it on a test set once. So this here, actually, I mean, this is already quite convenient because it wraps all the actual cross-validation in this function call here. But because this happens so often, we have a shortcut for that. No, okay. Questions about how this works, or like the concept? Maybe let's go through the concept. So the concept is, again, we started with a data set. We split the data set in a training part and a test part. We define a grid of parameters to search over, so let's say the number of neighbors. We use cross-validation and the parameter grid on the training data set to find the best parameters. Then we retrain a model using the best parameters on the whole training set and do a final evaluation on a test set. Questions?
Is there an optimal relationship between the number of folds you use in the validation and the final test data set? Should they be equal, or does it not matter? Or
I don't.
Size?
Yeah, I think basically for cross-validation, people usually use 5 or 10. Because then if you do very high ones, then other weird statistical things happen. So 5 or 10 is usually good, and test data is usually between 10 and 30%. But I don't think there's a relation. All right. So let's run through this in the notebook. Ooh. Does anyone know when the session ends? 1? OK. Other question?
Yeah, earlier when we were talking about stratifying, doesn't that also apply when you decide the cross-validation process?
Yes. So stratification also applies inside the cross-validation process. Actually, if the model you give cross-validation is a classifier, it will stratify by default. And in this notebook, I'll show you how to turn it on and off. OK, so I open the cross-validation notebook. Sorry. So first, I'm going to talk briefly about how to do cross-validation. So I loaded the digits data set, split it into training test set. And here I got my k-nearest neighbor classifier. And we have the cross-val score function, which takes as a first parameter the model, second parameter the data, third parameter the labels. And then it'll train the model using cross-validation and return the scores. So here I set CV equal to 5, which means do 5-fold cross-validation. It returns 5 accuracy values. So if I say CV equal to an integer, and it's a classifier, it will do stratified cross-validation. If it's a regressor, it will not do any stratification. So if it was a regression task, it would do like plain cross-validation. Also, by default, cross-validation does not shuffle. If I run this 5 times, it'll give me the same result 5 times, because there's no shuffling in this. You can have more control over how the cross-validation works. So if you're new to this, don't worry about it too much. If you're more advanced, here's how you have more control. Instead of CV equal to a number, you can give it an object. And there's many different ways how you could do splitting. Maybe I'm going to talk about this in the afternoon a little bit more. We'll see. So the two kind of obvious choices are k-fold, which just splits the data into k parts, and stratified k-fold. And so if I say I do classification, but I don't want to stratify, I can pass a k-fold object, which has this parameter number of splits, whether I want to shuffle, and if I shuffle, also the random state. So now, if I change the random, so this will now always give the same result, obviously, but if I change the random state, then it'll give me different results. Same for stratified. So I can decide whether I want to shuffle or not, whether I want to stratify or not. I can also, actually, there's repeated. Did I run this? I didn't run this. And there's I think we have at least 10 of these cross-validation strategies. But usually, if you just do CV equal to a number, and the number is 5 or 10, then you're fine. But you should be aware that it does not shuffle by default. No. There's none of this. Okay. Yeah, so repeated just does it the thing multiple times with different randomizations. Yes. So this evaluates only one parameter setting. This evaluates just the default parameter setting, which is number of neighbors equal to 3. And we now, if I ran this here, now I think I trained 100 models on different splits of the data. So now I'm very sure after this I can compute the mean of this. This gives me a very good accurate of how this particular parameter setting works. But we didn't tune the parameter setting next yet. That's the next line. So cross-validation, so that's something that I'm not sure if it's machine learning books or machine learning classes that mess this up. Cross-validation has nothing to do with searching over parameters. Cross-validation is just for evaluating a model in a robust way. A lot of people identify cross-validation with parameter search, but they're completely not related concepts. Okay. So now we know how to evaluate a single model. And now we can combine this with the grid search. So grid search is basically just a brute force search over parameter values. It's implemented in scikit-learn in a class called grid search CV. And we're going to use a model that's a kernel support vector machine. If you don't know it, don't worry about it. It has 2 parameters that you need to adjust for best performance. And the 2 parameters are called C and gamma. We could have also done the nearest neighbors here and K, but I think that's the exercise. Yeah, that's definitely the exercise. So here, the parameter values in this are C and gamma. So if I look at the help, you will see that there's a parameter called capital C and a parameter called lowercase gamma. And these are the ones we want to tune. To tune them, I need to specify a dictionary where the keys are the parameter names, and the values are lists of parameters to try. And so here I defined this, this dictionary, 2 keys with 6 values each. What grid search will do, it will try all possible combinations in a brute force way and try to find the best combination. And for each possible combination, it will run cross-validation to evaluate how good it is. So grid search is actually not implemented as a function. It's implemented as a model, basically. We call these models in scikit-learn are called estimators. And grid search is what we call a meta-estimator. I give it an estimator, here the support vector machine, SVC. And it'll create a new estimator that will use this model, but it will also automatically tune the parameters. So here I instantiate grid search with the support vector machine, the parameter grid, I tell it to be verbose, and I tell it to use 5-fold cross-validation. So now, this grid search object is a scikit-learn model. It behaves exactly like the things we looked at before. It has fit, predict, and score. So now, I can fit it on the training data. So remember before, I split my data set into a training and a test part. Now I use the training part to fit the grid search. So what this does is, in the background, it runs grid search with cross-validation. So you can see here that it tries the first parameter setting, which is this, c equal to this, gamma equal to this, 1, 2, 3, 4, 5 times, and then goes to the next parameter setting. This is because it's 5-fold cross-validation. So there are 5 models trained with this parameter setting, and then goes to the next parameter setting, trains 5 models with that, and so on. And that happens automatically just if you call fit. Okay, because I made it verbose, it now outputted a lot of stuff. Why is this so slow? Something is, okay. This is really, something really bad is happening somewhere. But I'm not going to figure it out today. All right, so now we fit the model. Now I can call predict. And so what fit also does, so it does all the cross-validation. It finds the best parameter setting, and then it retrains the model on the whole training set I gave it with the best parameter setting. So this call to fit basically does everything on this diagram automatically, which is kind of nice. So now if I call predict on the test set, it'll call predict on this model trained on the whole data set with the best parameter settings that were found.
Question. Why do you separate the parameter search from cross-validation?
Because they're completely different things.
Yes, but isn't the purpose of cross-validation or validation in general is finding the optimal parameter?
No. Like, there's more reasons to validate how well a model does, except in addition to searching parameters. You want to know, it's just, cross-validation answers the question, how good is this model? That's the only thing cross-validation says, how good is this model? The purpose of, like, I can think of other ways, like, why I want to know how good the model is. For example, I want to know, can I put this model in production? I might use cross-validation to say that. It has nothing to do with tuning the parameters. Okay, you don't believe me. Cross-validation is evaluating a model. That's it.
Yeah.
What does that have to do with tuning parameters? Okay.
It's kind of tied together.
Well, I don't think it's tied to the other, and I think it's a really bad job that a lot of people do in trying to teach what cross-validation is because it's a completely independent concept. But, well, maybe we disagree on that. It's fine. All right, so I can also call the score method and see how well it does on a test set, and it does really well. So, I mean, this is like a pretty simple data set, but so now after tuning the parameters, we have a really good model. And so now, you can see from this, actually, I didn't need to know what parameter setting worked well. It did everything for me automatically. If I want, I can inspect it, though, because maybe I'm interested in understanding my model, and can find best params. It's an attribute of the grid search, and it tells me c equal to 1, gamma equal to 0.001 was the best parameter setting. And I can also look at the best cross-validation score. So this is the best, this is the mean cross-validation score of the parameter setting that was selected. So actually here, for some reason, noise in the data set, whatever, the score is actually lower than a test set score. Usually we would expect this best score to be higher than a test set score, because this is what we use to tune the parameters. Finally, if I want to inspect the model, let's say I want to look at the coefficients of the model that I trained, I can look at best estimator. This just gives me back the model that was trained. The support vector machine doesn't have coefficients, but it has like dual coefficients. So if I wanted to look at the model, I could look at best estimator. But really the takeaway is you don't actually need to do any of these. You can just call predict, and it'll do the right thing. If you want to understand more what the model of what the tuning did, you can look at CV results. CV results is a dictionary that, among other things, contains the mean test score. And for each parameter, it contains actually the score for each of the folds. Right now I'm looking at the mean across the folds for the two parameters. And so here this is a visualization of the grid, how well the model performed as a parameter of C and gamma. So here brighter means more accurate, and the dark blue means actually very not accurate. So you can see that it goes from high 90s to like 10%. So this model is really, really sensitive to setting the hyperparameters. Like if I change the gamma a little bit, it goes from nearly perfect to chance performance. Sorry. One reason why you might want to look at this is if the optimum is like in a corner, that means you might want to expand your search space. So this will help you think about whether you want to expand your search space or you want to narrow down your search space. All right, so now I want to give you like 10 minutes to, as an exercise, use this to adjust the number of neighbors in the k-neighbors classifier. And you can do this on the digits data set or the iris data set if you want. Yeah?
At some point there was a parallel flag. I saw that on reading at some point. When you were choosing parameters, did you comment on that?
I never used it, right? Well,
Yeah, that's the parallel job one.
there's n jobs, yeah. So you can do n jobs, and then a number of processors you want to use to do the thing in parallel. If you do -1, it'll use all available processors, but it might mean that you don't have any processors left to move your mouse. So I would use usually like less than your number of actual processors. And this is embarrassingly parallel, so basically each algorithm will work on just one core, but you can do different parameter settings on different cores. Sorry. All right, so I want to give you 10 minutes to play with this. Or,
It's optimizing for accuracy, right? But is there a way to optimize for something else? Like
yes, so the question is, this optimizes for accuracy. Can I optimize for something else? Yes. There's a parameter called scoring. And, wait, I want to see, do we do this in the next slide? Okay, no, this is actually in the afternoon. But you can do this. So scoring can be a string, or it can be a metric that's a callable. And you can either come in the afternoon or look at the documentation to find out more about it. But there's like a lot of different ways you can do it. So again, for here, accuracy is the default for classification, and R² is the default for regression, but there's like many different choices. But you need to have a metric that puts out a single number. So you can use area on the ROC curve, but you can't use a ROC curve, and you can't use confusion matrix because it's unclear whether one confusion matrix is better than another. You need to have one number output.
So, what is the point of doing the grid search if you just, is that the same thing as
Yeah, it's exercises to do this, but with grid search CV.
Okay, but it's essentially the same thing.
It does exactly the same thing, yes,
Right.
only it's 10 lines less code.
Okay. Got it.
Excuse me? Are you bored or lost? Okay. So lost, okay. Because the question is, do I need to go faster or slower? But probably slower, okay.
Is there something missing here? We have not said what is the neighbors? How long will this run?
Oh, this is, if you go 2 slides before, 3 slides. Okay, maybe to say this again, don't copy what's on the slide, use grid search CV. Like there was a slide earlier how to do this, but that was like a way too complicated way of doing it.
Can you scroll a little bit down?
So we're just passing the parameter grid inside of the paren of the k nearest neighbor here, the classifier. So you're saying check the 2 k nearest neighbors for the different number of
Yes.
So the parameter grid would just be the number of
Neighbors, yeah. A dictionary.
And it just has like.
As key, the parameter value.
I'm sorry.
As the key is the name of the parameter you want to tune, and the value is a list of values you want to try.
I see.
So, verbose to 0. Or just remove it. Mm-hmm. Yeah, it labels 0 to 9. Yeah.
Oh. And then the X, it's a big X because it's always a matrix.
Yes.
Which is specific to scikit-learn. You're saying that data is always in the matrix.
Yes. I mean, that's like generally how most, I mean, it depends on the application. In text, it would be different. But yeah, in scikit-learn, it's always number of samples times number of features, numeric matrix. Yes. No, I think it's after this. Text is in the advanced one, I think. Yeah, that's, yeah. None of the algorithms accepted. There's an imputer, which basically right now only does median imputation, which is like the cheap strategy, which you can basically use as a preprocessor. It's a transformer. You can do fit on imputer, then transform, and then it imputes the data into any of them. No. Like basically none of them does anything, any preprocessing. You have to do everything explicitly by design.
For example, when you score it, we would get a higher score than when we look at that score. What's the difference between the two?
Oh, so this is the cross-validation. This is the cross-validation that happens through the search. So the search runs for each parameter setting a cross-validation, right? And this is the mean cross-validation you get for the best parameter setting. So for the one run where you set a neighbors equal to 9, this was the mean cross-validation score.
Okay, so this is just for the parameter search.
Yes.
But this is for actually the model itself.
Yes. I mean, this is for the final model, yes. So this is like the average over, depending on 5 or 10 different models.
I understand. So for parameter search, averaging out all 5.
Yeah.
This would be, the grid search tested on the train set.
Yeah, but doing cross-validation on training set. So ideally, these two numbers would be close together. Usually, you would expect this number to be higher because you did the maximum over all possible parameters.
Yes.
But because the data set is small and so on, depending on how you split your data set, this might be higher too. So the thing is also, you should look at the test data set only once, whereas you can look at these scores arbitrarily many times. But they're usually an overestimate of. So you can use them to tune your model, and then look once at the test data. Well, yeah, but you can overfit the parameters. So, I mean, you can tune, but then in the end, you should look once at the test set to make sure that, because cross-validation does not actually prevent you from overfitting the parameters.
Right.
It only makes it harder, but it doesn't. Ooh. Who needs more time? Who's still working on this? Who's done? Who's reading emails? Okay, if you're done, you can read emails. It's fine. Okay, I think we're going to move on because we don't have that much time anymore. So I also did a little plot afterwards. So important question is, how do you know which parameters to specify in your grid? The answer is read the documentation or ask a machine learning expert. Unfortunately, I don't think there's like a really good resource, and there's also not good benchmarks on what are good parameter settings. It's like a very slowly evolving field that's just happening right now. Anyhow, so you need to specify a dictionary. The key needs to be n neighbors, so the name of the parameters you want to tune. Then I said I want to try 1, 3, 5, 7, and 10. Then I instantiate the grid search with the k-neighbors classifier and the parameter grid. Actually, what I also did here to get a little bit, to do more inspection of what's happening, I'm going to tell it to also give me the train scores. Maybe I should have also set CV equal to 5. By default, it's 3. I prefer 5. I fit it on the training set. Then I look at what's the best parameter setting. Best parameter setting is 1 neighbor. The training set accuracy is 1, which is always the case when I use only 1 neighbor. And the score on the test set is nearly 1. Then I also plot the mean training and a mean test score as plots. So here we have only 1 parameter. Before we had 2 parameters, so you could visualize it as a heat map. Here we have 1 parameter, so it makes sense to visualize it as a line plot. If you have 3 parameters, good luck by a 3-dimensional monitor. No, I mean, you can do like different aspects of the plot, but 1 and 2 parameter settings are much easier. And so you can see that both go down as a function. So the optimum is clearly at 1. And then if you use a higher number of neighbors, both just go down. But as we sort of, if you listened earlier, basically the left one neighbor is a very complex model, so you would expect the difference between training and test set to be biggest. If you go to a simpler model, then the difference in the performance shrinks. Okay, questions? No, all right. Yeah?
Is the code to plot these online somewhere? Or are these solutions available?
They were available last night at 8. Wait, oh no, they were not, because I didn't have Wi-Fi. Yeah, I'm sorry about this. The problem is now they're all filled. No, I ran them all, so I don't want to push them now. I'm going to push them in lunch break. Sorry about that. I forgot to push last night. I was a little bit tired. Okay. So let's go on, and let's talk about preprocessing. Wow, last year I was way faster. Yeah. Okay, let's talk about preprocessing, because a bunch of people asked me about preprocessing. So one of the things is that scikit-learn doesn't automatically do preprocessing, so you have to do all the preprocessing manually. And but preprocessing can be really important. So for example, here, this is a regression data set without preprocessing. And you can see that, well, maybe if you look in really closely, that the different variables have very different ranges. So this one here goes from 0 to 90. This goes from 3 to 9. This goes from 100 to 800, and so on. This is the Boston housing data set, which is about prices of houses in neighborhoods in Boston in the 70s. So they're all like $3,000, and I wish I lived then. So here's just a box plot of these. This is like different properties like crime rate, industrialization, nitrogen carbide, how old the houses are, and so on. But you can see these are widely different distributions and widely different ranges. And depending on your model, having widely different ranges might be a big problem. So tree-based models don't care at all. For tree-based models, the range and actually also the distribution of the data doesn't matter at all, which is one of the cool things about tree-based models. So if you use gradient boosting or random forests, you don't need to scale the data. But if you use a linear model or any distance-based model, then it's a big problem. What's that? So there's no score here. Okay, so here's how you would do. I think we have a comparison later, but here's how you would do scoring. So Ridge is just a linear regression model, and so here I use the standard scaler we saw before to scale the data. So I scale the standard scaler on the training set. I transform it. I fit the Ridge model on the scaled data set, and then I transform the test data with the scaler, and then I do score. So this is sort of, in the afternoon we'll see a quicker version to do this, but basically here, I have two steps. I have the standard scaler, I fit the standard scaler, I transform with the standard scaler, then I fit on the transform data, then I transform the test data, and predict on the transform data. So this is like scaling is sort of one of the main preprocessing methods that are important for many models. So there's, I don't know, there's like 6 different scalars now. I think the most commonly used ones are standard scaler, which is 0 mean unit variance, and min-max scaler. Min-max scaler scales everything between a minimum and a maximum, usually between 0 and 1. If your data has like natural boundaries, like the images always have values between 0 and 255, then min-max scaler might be a good idea. For most data sets, a standard scaler is a good idea. Also, if your data set is always positive, maybe min-max scaler might also make more sense. There's also a robust scaler, which works like the min-max scaler, but uses the mean and quantiles instead of mean and standard deviation. right now, it's kind of hard to use different normalization on different features. In the next version, it will be really easy. Come again next year, and I'll show you. Sorry, I think it should be easy, and in particular, very often you have a mixture of categorical and continuous values, and you want to treat the categorical and the continuous differently. And so there's a thing called feature union in scikit-learn, which allows you to do this. But right now, taking a subset of the columns is like, you need to write some custom code to do that. And so, soon it will be better. But that's unfortunately all I can say. So there's an example called heterogeneous feature union on the scikit-learn website that tells you how to do it right now, but it takes a bunch of code. So the other thing that's kind of very important in pre-processing is dealing with categorical features. So far we assumed everything was float. But what happens if you have a categorical feature like the color of a dress you want to sell? That's not a number. And so how do we encode this? So the simplest thing you maybe can come up with is, OK, I just number them. Red is 0, green is 1, blue is 2. If you do that, then you created an ordering and the distance between them. You said green is between red and blue. And depending on what these categories are, it might make sense or not. Usually you want to avoid this, because usually there's no natural ordering and no natural distance between them. So the way that they're most commonly encoded is with what's called one-hot encoding or dummy encoding, where you create a new feature for every possible value, also called level, of the categorical variable. And you set this always to 0, except for when this is the actual value. So to encode three data points, the first one has the value red, the second one has the value green, the third one has the value blue. This is how I would do it. There's 3 different possible values for this categorical variable. I create 3 different features. And set the one that is the actual value to 1, the others to 0. So you could theoretically leave out one of them, and there's an option to do that. So they're linearly dependent. So if I know red and green is 0, I know blue will be 1. If I know red or green was 1, then I know blue will be 0. So you only need a number of levels minus 1 many. But depending on the model, which one you leave out might influence the result. And sometimes it might make the results harder to interpret. So if you're only interested in prediction, having linear dependence in the parameters, in the variables, is not really a big deal. If you're interested in p-values, it might be more of an issue. But because I'm interested in prediction, I don't really care. But so you can do either one-hot encoding like this, or you can leave out one of the values. Obviously, it's important to know beforehand how many different values there are and what they are. So let's walk through the pre-processing. So yeah, I want to demonstrate these 2 pre-processing things, the scaling and the one-hot encoding. So here I'm going to use, for the scaling, the Boston housing data set. So here's a description if you're interested. Yeah, it's like a small, old classical data set. It's from 78. And there's, I guess, 12 different features. So here, always the features on the x-axis, and the target outcome, the median value, is on the y-axis. And so this is just to illustrate the different ranges and different distributions. Here's the box plot again. And so in particular, there's tax and B that have like much, much higher ranges than everything else. This one here is actually a very important variable, but it's just a 0, 1 indicator. So it's a much, much smaller range. So now what I'm going to do is actually I'm going to compare using scaling and not using scaling, using cross-validation. So here's the use of cross-validation without grid search. But so I scale the training data, and with standard scaler, I have cross-validation, and I run the k-neighbors regressor on the original training data and on the scale training data. And so this is R squared. This is the mean R squared of the cross-validation with and without scaling. And you can see that there's a pretty big difference in performance. The problem, the issue is with nearest neighbors. Nearest neighbors is based on Euclidean distances. And so if one thing has a range in the hundreds, this will be the only feature this will be taken into account. So because if one data point has a value of like 450 and another one of 456, there will be 6 different, like by 6. If another one only have values 0 and 1, there can only be 1 different. So the difference between the thing with the large scale will only be much, much bigger than the ones with the small scale. So this is a model that will be completely thrown off by scaling. So if instead, I mean, I can just do this quickly maybe. Oh, let's do random forest. So the random forest is a tree-based model. So if I fix the random seed, the score should not change, or maybe the tie breaking might change. No, why? Oh, it's a regression problem, not a classification problem. So this was the scaled data, and here's the unscaled data. And you can see that it's, so there's some numeric issues. So you can see here after the 4th decimal or something, there's like slight changes, but basically the model doesn't care. So if you have a random forest, if a tree-based model, scaling not important. If you have a distance-based one like nearest neighbor classifier, any linear model, or any regularized linear model, or like a support vector machine, scaling makes a huge difference. All right. Questions about scaling? So the next thing I want to talk about is categorical variables. So we're actually also working on making this a little bit better inside scikit-learn, but right now I would actually recommend doing the pre-processing with pandas. So let's say I have a data frame here that has like categorical variable, which is the borough of Manhattan someone lives in, and then we have a salary, which is an integer. And so pandas has the method called getDummies, which will just automatically expand the dummy encoding. And it does this for everything that has an object d-type. So that's usually, depending on how you do it, that's usually the strings. So you can see it automatically expanded the borough, but not the salary. It also just has the parameter to, I think it's called drop first. This will drop the first level. So now you wouldn't have redundancy in the encoding. So, but what happens if someone was very helpful? It happens often that people that encode the data are very helpful, and they don't encode the data as strings as we did there, but they encode it as integers already. So now someone like labeled Manhattan 0 and Brooklyn 1 and so on. And now if I call getDummies on this, nothing happens because there's no string features to encode. But I can also explicitly say which column I want to encode with the columns parameter. And so I say columns equal to borrow, and then borrow, which is an integer, will be encoded. I don't want the salary that's also an integer to be encoded, because then I would get like a new feature for each unique value of salary, which doesn't make sense. So here you can also see it's important to know the semantics of your features. Even though both of these here are integer features, we know that one of them we should treat as a categorical, and one of them we should treat as a continuous. And we can only know this by knowing the semantics of it. Yeah?
So basically, in our training model, they don't understand text. So all those things like words, things we have to basically convert it to
Yes. You need to so scikit-learn always only works on numbers, except for the things that explicitly work on text. But there's text and there's categorical variables, which are somewhat different. In the afternoon, we'll talk about how to process actual text data. But if you have only fixed values, then you probably have to deal with the categorical, where you have like a list. These are all the possible values, and then you can use one-hot encoding. If you have like a tweet or an email, that's something different. But though it's not always as clear-cut, so I had when I was working at Amazon, I was actually working on like dresses for shopping, and there was a color field, and the color field, you would think color is categorical, and I wish it was categorical, but then there's some of the sellers puts in angry panda, and I was not really sure how to deal with that. How do you map that to a color? And so you can't really say that you know all the possible colors, but you can. So if you have a free text field, even if you think it should be categorical, well, first, if you design the data collection, if you're lucky, don't give users free text fields. If someone else made this mistake, then probably you need to do some manual cleaning to map it back to something that's more semantic. So what I also said before is that you need to know what are the possible levels, what are the possible categories that can happen. Because let's say someone has this data set, and someone else has a different data set that has also 4 borrows. So for those people not from New York, which is probably nearly no one here, there's 5 borrows. This data set only has 4. So let's say I have a different data set which has also 4 borrows, but it's not the same 4 borrows. Then the features might line up, but they will have semantic differences. So I need to have a list of all the possible values so that the semantics are aligned every time I transform the data. So if someone else would give me a new data set and I did a separate encoding on this data set, I might get something that is not aligned with this here semantically at all. The way to get around this is, so here I create a data set. So the first line here creates a data frame again. In the second frame, I tell it this borrow is actually not a string, it's a categorical variable. And I know what the categories are. These are the categories. There's 5 categories. And so now pandas will know, okay, the representation looks exactly the same, but actually it will only allow one of these values, and it knows how many values there are and what they are. So if I call get dummies now, it'll add a column for each possible value. So if it doesn't matter which values actually appear in this data set, I will always have a consistent encoding if I gave them in the same order, because it respects the order. So that's still like a caveat. Maybe I should have sorted them. But so as long as I give the same categories here, I will get the same features out, even though Staten Island didn't happen to appear in this data set. This seems kind of trivial, but this happens all the time and messes up analysis all the time. because you have a new value, maybe you've never seen this value before, or another value didn't happen. So here, yeah, so the way to do this is you can assign the column with S-type category and then the categories. And then getDummies will know exactly what to do. Otherwise, it just guesses what the strings might mean. All right, so what I want you to do is now load the data set. It's the adult data set here. It's a data set from the, I think, 1990 census, maybe 92, of US adults and their income. So there's a binary response variable, which is whether they make 50K a year or less, which in the 90s was whether they make a lot of money or not. And so please load the data set, do the one-hot encoding, and then do the scaling. So right now, because it's kind of tricky to separate the categorical from not categorical, just scale everything. Like just run everything to do the one-hot encoding first and then do the scaling. If you want, you can also just get a subset of the columns, because there's many columns. And so you can think about whether it makes sense to look at all of the columns. Actually, I think in my solution, I only picked out some of them. And you can also visualize the data and look at the data a little bit. This data set doesn't have missing values, but other than that, it looks like sort of real data. It's slightly messy. So I want to give you 10 minutes for that. All right, so maybe let's come back and check out the solution. So here I just read the data set. I look at data.head. So what the display does is just shows you the stuff. It's the same as if I just wrote it in a single cell. So just see the output. So this is sort of how the data set looks like. Head shows me the first 5 rows. And you can see that there's most of them are like string variables that are probably categorical. There's age, work class, education encoded as a numerical, marital status, occupation, and so on. Capital gain, capital loss, hours per week, and age are probably the only, and education numeric are the only numeric variables. And the other ones, they have like a lot of different levels. So what I'm doing is now, because the goal here would be to predict income, or whether the income is greater than 50K or not, I'm going to take out the income variable and store it separately, and then drop it from the data. And so data features is now only the things that I call, that I consider my input features. OK, then I checked if I did it correctly, and I did. So here, this is the thing where the income is not included anymore. Then I call getDummies. I don't want to dummy encode the income. And then I split the data using the one-hot encoded, or dummy encoded, and the income. So here now, xtrain, xtest are the splitting of the one-hot encoded data. I used the min-max scaler here, I think because I didn't want to mess up the zeros and ones because there's so many categoricals. You could have also used the standard scaler. Probably doesn't matter that much. So I fit it on the training set. Then I transform a training set. I get xtrain scaled. Then I get to look at the shape of xtrain. So xtrain is now pretty big. It has 107 columns because of all the different possible values. I also called bin count on y, or value count. So you can see that it's a pretty imbalanced data set. There's about 1,800 people making less than 50K and about 6,000 making more than 50K. And then finally, I looked at all the ones that have the data types as integer. So these are all the ones that are continuous. And I'm going to do a scatter plot for only those. So here, I look at only the continuous columns, and then I do a scatter matrix. And so here I can maybe see that people that have, wait, orange means what? Orange means less than 50K, right? So if you have capital gains, then you probably make more than 50K. So the people that have higher capital gains usually make more than 50K. And even the capital loss is correlated with, so if you trade at stock at all, you probably have more money. Like poor people don't have losses because they don't trade. Anyhow, so this is like, and people that are older are also more likely to make more money. And people that have more hours per week are also more likely to get more money. All right, so this is like the most, and now we could learn a model on this because now the X-train that we have, no, X-train scaled is now in the format that we want. So someone also commented like basically all of scikit-learn, or nearly all of scikit-learn, everything but train test split, gets rid of the pandas column names. So the output will always be a NumPy array. So here, this one doesn't have the column names anymore. The shape of this, still the columns correspond to the what's it called? Is it called X-train? The columns correspond to the one that were in X-train. So I can still figure out in X-train scaled, like the first column is age, the second is education, now, and so on. But X-train scaled itself is a NumPy array, and using the scikit-learn scaling got rid of the column headers.
Do we need to categorize the class label in this case?
Sorry?
Do we need to categorize the class label in this case? It is less than 50K and it's more than 50K. Is that need to be categorized?
Well, yeah, it's categorical, but it's so the class labels are expected to be categorical, and they're treated by the classifier. So if you apply a classifier, it'll be fine. You could make it 0 and 1 if you wanted, but it doesn't really matter. So any classifier will work on this, any scikit-learn classifier.
So let's say if a class label in here is have a, let's say, for range from 0 to 25, 25 to 50, 50 to 75, 75 to 100. So as long as it's categorical, it still can fit into this thing.
Yes. Yeah. But it's like, so this is, if you do this as a binary classification problem, the semantics of these labels are completely lost. It will just be a binary classification problem. If you make more bins, like from different values, and you make a classification problem, the classifier will not know about the ordering, right? It will be completely independent classifications, which is maybe not what you want.
In this case, this is a binary classification.
Yes. No, you can just discretize it more, but just be aware that if the discretization, if you make it as a classification problem, you will lose the information that the bins are actually ordered. All right, so get half an hour more. So I'm probably just gonna continue doing this, the material from now in the afternoon, and then see in the afternoon how far we get. I guess we're going to do the linear models now for regression, and then linear models for classification, and so on will be done in the afternoon. And you can stick around if you like, or go somewhere else. So for linear models for regression, so now I want to talk a little bit more about particular models. So first linear models, then tree-based models. So just a very brief recap of how linear models work. So this is one of the most simple kinds of machine learning models, except for nearest neighbors, basically. But they're actually very useful, and they're widely used, particularly for high-dimensional data, for sparse data, for text data. So if you want to do regression, so you probably remember least squares from high school, or I guess in the US it's college. No, it's true. So what we're trying to do is here we have one input feature on the x-axis and one output on the y-axis, and we try to fit a line to it. And so in 1D, this is just fitting the slope and an intercept, which you call W and B. If you have a higher dimensional input, so if you have more than one input feature, what we're trying to learn is for each input feature, a slope, which is 1W, and there's just one separate B, that's the offset. And so we can write this as like an inner product of W transposed X, or just as a sum over all the features, and each feature has a weight, which is the slope in this direction. And so the parameters of this model are very simple. They're number of feature many W's, and then there's a B. So in 2 dimensions you have, in 1 dimension you have 2 features. In 1 dimension you have 2 parameters. In 2 dimensions you have 3 parameters, and so on. And so the goal is now to fit these parameters so as to fit the training set best. So the simplest way to do this is with ordinary least squares. This is usually called linear regression. And so here, what we're doing is we just sum over all data points. So here the sum, no, there's a mistake. OK, so the second sum is supposed to be the sum over all data points. Sorry, it's not supposed to be the sum over all features. So we sum over all data points. For each data point, we check how close is WXI to YI, and in the least square sense. So how well does a W transpose XY approximate YI? And we sum this over all data points. And we want to find a W that minimizes the squared loss. And this is a training procedure for ordinary least squares or linear regression. And so if the data set X has full rank, then this has a unique solution. And so this is like, OK, you can run a numerical solver, least square solver, convex optimization solver, whatever you want, and it'll find you this W. And this will represent this line. So this is a little bit problematic for 2 reasons. So A, you need to have the data set be full rank, which is not always the case, and which you can't always control for. And also, this has no parameters between the complexity. So there's like, the complexity here depends on the input dimension. So the more features you have, the more complex this is. In particular, if you have many more features than data points, which often happens in practice, like if you have a very high dimensional space, but like let's say you look at the genome and you have 100 subjects, but the genome is longer than 100 base pairs, then there's many solutions. The solution space is huge, and it's very easy to fit any possible function perfectly. So high danger of overfitting if you're in a high dimensional space. So there's an improvement upon this, which is called rich regression, which is penalized linear regression. So here we add another term to this minimization. So we don't only want to fit the data well, we also want the model to be simple. And this model being simple is expressed as this plus alpha norm of W. And so what this basically says is I want the slope to be small in all directions. So I want few of the feature, or I want the features not to, I want the output not to depend too much on any of the features. I want all the W's to be small. If you set, and the alpha here is a tuning parameter. So if you set alpha to 0, you have you have the ordinary least squares. If you set alpha to infinity, you get a solution all zeros. So the higher you set alpha, the more simple the solution you get. This way you can control for overfitting. This will always, if you set alpha unequal to 0, it'll always have a unique solution. And so this problem is also easier to optimize. And so if you have a very low dimensional problem, if your number of data points are much higher than your number of features, the standard linear regression will work well. If you have a higher dimensional problem, you probably want to use a ridge regression. So let's check this out in the notebook. So we're going to use the Boston data set. What happened here? Okay. The Boston data set that I showed before, which is this house price data set in Boston. And we're going to look both at ridge and linear regression. We're also going to get cross-validation to compare some different models. So why did I shuffle? OK, I actually didn't need to shuffle. OK, so the Boston housing data set has 500 data points and 13 features. So actually for this, probably linear regression will work well because you have quite a few more data points than you have features. So here again is the plot, 13 features, and 500 data points. So we do a train test split. And now we can look at, if we do tenfold cross-validation, how well does linear regression do? And how well does ridge regression do? And they're relatively comparable. Ridge regression does slightly worse. But they both have an R-square of around 0.71. So what we can do now, the first thing we might want to do is tune the alpha. So there's some alpha in this ridge. I think by default it's 1. Yeah, it's 1. And so now we can try to tune the alpha parameter and see if we can get better. So, tuning regularization parameter is usually a good idea to do this on log space. It's similar to what we did earlier with the support vector machine, where we tuned C and gamma. They were also on a log space. So here, maybe I should have used different. Well, yeah, so it goes logarithmically from 10 to the minus 3 to 10 to the 3. And I can run grid search. And they look at the mean train score and mean test score. They look like this. So here on the x-axis is the parameter alpha, and on the y-axis is the accuracy. Can anyone tell me what this means? So this is on a log scale. So this is like really small values of alpha, and this is bigger values of alpha. Something bias variance, yes. So I mean, you can see that increasing alpha kind of decreases the distance between training and test set, but also makes it worse. In particular, like the smaller I make alpha, the better. This means ridge regression here doesn't help. Basically, setting alpha to 0 seems like a good choice, according to the cross-validation, which is a little bit what we would expect because we already ran linear regression and it also gave a good result. So here, grid search tells us that basically setting alpha very small is probably the optimum. So now what I'm going to do is I'm not doing it properly, but apparently, according to my comment, I'm not doing things properly. But so what I'm doing now is I actually do an expansion into a polynomial basis. Polynomial feature allows me to add interaction features between all pairs of features, and also it adds polynomials. So by default, it adds second-degree polynomials. So for each feature, it will add x squared as that feature too. I scale the data before, and then I do this polynomial expansion. So now I have 104 features because I looked at all pairs of features and created a new feature for them. And for each feature, I also added the square of that feature. So now I'm in a very different situation. Now the number of features is quite close to the number of samples. So now I'm much more in danger of overfitting. So now we can run the same experiment again. So actually now, both of them do much better. So adding these interaction features helped a lot. But now linear regression is slightly worse than ridge regression. So we can expect that ridge regression, so the regularization of ridge regression actually helped. So now again, we can tune the parameters, because like even with the default parameter, ridge regression helped. So now we can think maybe if we tune the parameter, it's actually gonna get better. And you can see here, there's a pretty clear curve. So this is this looks pretty much exactly like the cartoon I showed you earlier, only flipped. So here, if we do, if we have a very complex model, so alpha very small, I get high training score, but low test score. They come closer and closer together. If I make the model more simple, there's a sweet spot here, and if I make the model too simple, both of them will go bad. And you can see the sweet spot here is about 10 to the power of 1, so about 10. So if I set alpha to 10, for this model, this data set, that's a good trade-off between overfitting and underfitting. Okay, I can also look at what best param is. Okay, it's like 14. Because I use a logarithmic scale, it's probably 10 is not in it. I can also look at what this does to the actual coefficients. So these are the W's. So here now how many? There's like 104 different features. So there's 104 different W's. And so this is doing linear regression. So these are all the features, the W's in linear regression. And what you can see is there are some really big ones. So there's 10 to the power of 13 times 0.2 and times minus 0.8. So there are two features that are giant, like sort of infinite, not really, it's like a billion or something, but with opposite signs. This is a sign that solving this was very unstable, and there's really bad overfitting happening. Whereas if I look at the same for the ridge regression, all the coefficients are between -3 and 3, and they look much more reasonable. So like having coefficients that are 10 to the 13, probably a bad sign. So not only did we get a better accuracy, we also got a much more reasonable model. We can also compare how do these coefficients look for different settings of alpha. And as you might expect, if you increase alpha, that means you penalize the coefficients for being large. So increasing alpha means the coefficients become smaller. So alpha equal to 1 was the default setting. Alpha equal to 14 was the best setting. Alpha equal to 100 is if you make even more regularization. And you can see basically how the points wander closer and closer to the 0 line if you increase the regularization. Let's skip this.
Is this like the opposite? This is inverse of C?
Yes. Alpha is exactly the inverse of C. Times number of samples, something like that. All right. So now maybe you can do this, the same thing and try to do linear regression on diabetes. On diabetes data sets, a different built-in data set. And you can try linear regression, ridge regression, maybe not lasso, maybe lasso if you want. But I would focus on linear regression, ridge regression, and visualize the coefficients and also see how the behavior changes if you add polynomial features. And yeah, so I think I'll give you like 8 minutes for this to play around with it and then at 12:50, we can like do some final questions for those that want to go somewhere else in the afternoon, and wrap it up. And then at, I don't know, whatever, 2 or something, we'll start back up.
Can you quickly touch on when you would opt for lasso versus ridge repair?
Okay, yeah, so I didn't actually put any details on lasso here, but there's a different way. I don't think I have a slide, do I? Not in this deck, no. Lasso basically penalizes W in a different way, which makes it sometimes exactly 0. And that's a good idea if you either want a very interpretable model or if you expect most of your coefficients to be 0. And if you don't think there's a true model in which most of the coefficients are actually 0, then it doesn't really make a lot of sense. And usually the best results you get if you use elastic net, which is a mixture of both of them. And if you just grid search elastic net, basically includes both of them, and you can get the best possible model. So I load the diabetes data set, and I put it into a data frame so I can do an easier box plot. So you can see that there's, so this is sort of, I think it's blood sugar, actually target. I should have looked it up. And so you can see that there are several features that come in. Actually, they're all relatively normalized between, their mean is around, or their median is around 0, and they're all between minus 0.1 and 0.1 mostly. The target distribution looks like this. Okay, seems like a reasonable data set. It's not too skewed or no crazy outliers. So, wait, do I have a, I also already fit a model with cross-validation, linear model with logistic regression, and with ridge. So I didn't give you the shape of X, did I? So there are 300 data points and 10 features, so maybe we don't expect regularization to be necessary. So the ridge model, that's somewhat worse than the linear model without tuning. So next thing, we can start trying to tune the ridge model or using scaling. So here the first thing I did was scale the data and then do cross-validation on the scaled data. After scaling, ridge and linear regression perform pretty much the same and as good as linear regression. So actually, linear regression is invariant to scaling, while ridge regression is not. So here you can see that the scaling actually made a difference for ridge regression and not for linear regression. But basically what this did was it made the regularization less because the regularization scales with the size of the data. All right, but so then I think I used, yeah, so with the scale data then I tuned ridge on logarithmic scale, and it told me regularization, like alpha of 10 is good, so some regularization was good, but the result didn't get significantly better. If you look at the performance here, you can see that, okay, if I add some regularization here, it gets slightly better. If I add too much regularization, it gets way worse. Yeah?
So in here we apply folding and multiple alpha value to loop through. Is that correct?
Well, first I did just cross-validation with the default settings and checked out what the default settings do. And then I did a grid search to find a good parameter setting afterwards. And then I never used a test set. I have some test set that I put aside that I haven't used it at all.
But the CD equal 10 means is folded to a 10.
Yes. So here, these ones are the result of tenfold cross-validation. So here I ran only cross-validation with a fixed parameter setting. And here I ran cross-validation within a grid search. So I tried out different values of alpha, and I tried to find out which one is best. So here just used alpha equal to 1 because that's the default, and I ran cross-validation with that. just to see what the default would do, and then I ran a grid search, which built like many more models. And like grid search found that here this is slightly better than here. Yeah, I guess then I looked at the coefficients of the optimum model versus the linear regression. You can see that some of the features that linear regression thought were important, which thought were not important at all. I didn't give it the names here, but there's like some pretty clear differences between, while some of the coefficients are the same. I also did grid search with lasso, which gave slightly worse results. And then I looked at polynomial features, and if I do polynomial features, linear regression gives a very bad result because I have so many features. Ridge regression gives about the same result as before. And then in the end, I tried grid search alpha for the polynomial features. I got alpha equal to 100, and then actually I get a worse score out than I did before. So polynomial features didn't help at all in this data set. It actually made things worse. All right. So now I'm happy to take any questions about this or anything else from the morning. I'll be around for a bit.